Welcome to the lesson 15 of the Advent of SysML v2. This is a training series consisting of short videos and exercises brought to you by Sensmetry in collaboration with Vince Molnár. My name is Kestutis, and today we are exploring feature evaluation with Syside the Automator. So far in this series we've been building models, defining parts, attributes, and quantities and their relationships. But there is critical difference between defining a model and computing its actual values. By the end of this lesson, you'll know how to evaluate simple and complex attributes and understand how evaluation scope determines the value you get. So what exactly is feature evaluation? It's the difference between looking at the blueprint and calculating what the system actually does. When you view a definition, you see reindeer has a weight attribute with default value of 110 kilograms. When you evaluate a usage, you compute this specific reindeer, Rudolph, weighs 100 kilograms. Why does this matter? In verification, you may ask, does your design meet the requirements? Is the total weight under the limit? Same for validation questions. Can you analyze system behavior? What happens when energy drops to zero? And for understanding the system, what are the actual values in this configuration? In SysML v2, evaluation is performed by computational tools. Syside Automator provides this capability. It lets you evaluate feature expressions and get computed values through Python scripts. Let's look at a practical example. Evaluating Rudolph's attributes. We are using the reindeer model from lesson 11. Rudolph is a specialized reindeer with overridden values, weight of 100 kilograms, energy level of 200, and of course that famous red nose. With Syside Automator, we can evaluate these attributes programmatically. For simple numeric attributes like weight and energy level, evaluation gives us direct values. Weight evaluates to 100, energy level to 200. Notice something important. Numeric values are returned without units. Thus, the values returned for quantities are automatically converted to SI base unit. Now, let's look at evaluation of complex attributes. Rudolph's nose color, eye color, antler length are specified using instantiation expression, grouping them under reindeer features structure. When you evaluate this complex attribute value, you get back a model element, not a simple number. Here's the evaluation pattern you need to remember. Simple values, like numbers and text strings, give you the value directly. Complex objects, like attribute structures, give you a model element that you can explore further by evaluating its own features. So, to get Rudolph's nose color, you first evaluate the feature attributes, then evaluate the nose color within that result. The result: nose color is red, eye color is brown, antler length is 0.6 meters, converted from the 60 centimeters automatically. Here is a useful capability: evaluation at different scopes. When you evaluate a feature, the scope determines which specialization's values are used. This is the mechanism behind how default values and overrides actually work. We can evaluate the same feature, the weight from the base reindeer definition, with different scopes to get different results. Evaluated with reindeer as the scope, we get the default value 110 kilograms. Evaluated with Rudolph as the scope, we get the overridden value 100 kilograms. So what is happening here? The scope tells evaluator, evaluate this feature as if you are in this type's context. This reveals something fundamental about SysML v2 specializations. Features are inherited. Rudolph doesn't have a separate weight feature, it inherits and redefines the one from reindeer. Scope determines values. The same inherited feature can have different values depending on which specialization scope you evaluate in. This is how default values and overrides work. The base scope gives defaults, specialized scopes give you the overrides. Understanding scope is essential when navigating part hierarchies and evaluating nested structures. You need to know which context you are evaluating in to get the correct values. In previous examples, we accessed properties like feature underscore value underscore expression to get evaluation results. But how did we know to use that particular property name? When writing scripts to work with your models, you often need to know exactly what you can access. How do you discover what other properties are available to you? This is where concrete syntax tree, the CST Explorer, comes into play. The CST is a structured representation of your SysML code that shows every element and its relationships. Unlike an abstract view that focuses only on semantics, the CST preserves the exact structure from your source code. Syside provides a free CST Explorer. You can paste any SysML v2 or caramel code and instantly see its tree structure. Here is how it can help you write scripts. When you paste your SysML code into the CST Explorer, you can see the parsed structure. An attribute appears as an attribute usage node. Its value is stored in a feature value node. The CST structure often mirrors what you'll access in your scripts. If you see a feature value node in the tree, you can expect properties like feature_value or feature_value_expression in the scripting interface. Without this tool, you would resort to trial and error or reading extensive documentation. With it, you can see the structure and make educated guesses about what properties exist. The workflow is straightforward. Paste your SysML model into the CST Explorer, find the node structure, and use those names in your Python code. Lastly, your new challenge task is to practice the feature evaluation. Check the blog post for detailed instructions and code examples. Share your experiences and feel free to ask questions in our community forum. Links and information on how to get access to Syside Cloud are available in the video description. Like, subscribe, and click on the bell icon to get notified about future lessons. Take care and happy modeling!